It's 3:30, so I think we'll go ahead and get started. Welcome back to the last session of the day. And this is session 5B, Utility and ISO Probabilistic Forecasting Developments. And we've got a fine lineup of folks from a number of the ISOs from here and there. Andrew, you're from there. Okay, and the session will be chaired by Tim Duffy, who's with the New York ISO, and Tim is active in this area as well. So Tim, let me turn it over to you.
Thank you. Thanks, Charlie. I just want to make a few opening remarks before I turn it over to the panelists who have the real info to present, and that's where the real bang is for this afternoon. I just want to set the stage for this panel, the Utility ISO Probabilistic Forecasting Developments. We've spent the last few days, or couple days, actually, some of us have been here since Monday, a couple of days discussing many of the challenges in wind, weather, solar forecasting, as well as load forecasting facing the energy industry. And the ISOs, the utilities, are really on the front lines in meeting those challenges, being the ones that are charged with essentially keeping the lights on. We understand well that the increasing uncertainty with respect to loads, as well as that's associated with, for example, electric vehicles, batteries, large loads such as data centers, such as electrolyzers, and in fact, behind the meter solar, again, impacting not only the magnitude, but also the variability associated with net loads. That is increasing at the same time that we're seeing on the supply side, increasing uncertainty, again, with the increased penetration of intermittent resources, wind, solar, and their dependency not on a pipeline, but on essentially the weather. And that's, again, something that we're very, very cognizant of as load forecasters and as members of the members that are supporting the operations side of the house. Operational risk is not something new to the energy industry or to the ISOs, RTOs, but it's something that is changing in terms of its complexity. Historically, we've identified risks associated with risk with contingencies, essentially, and in response to that, we've built out reserves, contingent reserves, or manage the system to N-1 or N-2 conditions. However, things are changing again, and we now need to focus on managing the risk associated with the uncertainty associated, again, with load and supply. So the folks that would be presenting today, this panel, they're really on the leading edge in this area. And so we've spent some time Monday going through a lot of what's going on. Very, very exciting developments, new and innovation is coming from these practitioners. And I'm very pleased to have them present today, and look forward to the discussion that we'll have as the afternoon draws to a close. So thank you very much for your participation, your attendance, and active listening, as they say. So with that, I want to turn it over to Andrew Akman, who is with the AEMO. He's come, I think, probably one of the farthest participants here today. And he's going to be discussing what's going on in terms of EMO, essentially the recent developments in probabilistic forecasting, and there's a lot going on down there. So,
okay, great. Can everyone hear me? Everyone hear me? It's on. Oh, okay. Yeah. All right. Okay. Great. Good afternoon, everyone. I'm Andrew Akman. I'm the principal data scientist with the operational forecasting team at AEMO, the Australian Energy Market Operator. I might just, so I feel like it's going to be better. Yep, great. So I'm going to be talking about recent developments that we've been doing with probabilistic forecasting. So I've definitely over-prepared some slides today, so I might, please ignore me if I skip through a few of them. But today, I'm going to give a very, very lightweight introduction into AEMO, and then we're going to dive into two really interesting developments that we're doing around the probabilistic forecast space. So AEMO. We are a member-based, not-for-profit organization. We maintain and operate the gas and electricity markets for almost whole country. I would say about 99% of the populace. And if we just kind of zoom in on our largest ERCOT, we serve a population of just under 23 million. We have a max demand of just shy of 36 gigawatts, and we've just received a new minimum demand record of about 11 gigawatts. Now, the reason that we keep getting new minimum demand records is that we have a very, very high penetration of behind-the-meter DPVs. So with approximately 3 million homes having a solar system, to put that in perspective, that's about 1 in every 3rd home in the country has a rooftop solar panel attached to it. So we have a lot of renewables coming on the grid. We have a lot of solar being coming on behind the meter. Right now, about 25% of our operational demand is being met by large-scale VRE. While we are currently still a coal-dominated system, we have a lot of planned retirements for most of our units, and already by 2030, we estimate that 80% will need to be met of our operational demand will need to be met by large-scale VRE, whether directly or stored. Now, there's a whole heap of interesting trends and challenges that I'd love to talk about today, but suffice to say, all of this is contributing to an increasing amount of variability and uncertainty coming into the network. Now, one thing that I seem to say a lot over the last couple of days is that we cannot forecast our way out of uncertainty. So we are looking to probabilistic methods as just one method as a way to help complement our deterministic approaches in order to kind of control and maintain all this increasing growth and uncertainty that we're seeing. So with that, let's dive straight into one of the ways that we're utilizing probabilistic methods. Now, last year, I was in Denver at this workshop, and I did talk a little bit about how we set reserves in the NEM. I did introduce a method in which we are actually dynamically setting our reserves based on probabilistic measures that try to account for uncertainty into the network. I don't have time to really rehash some of that again, but I did leave it on a note saying that some of these methods probably didn't go far enough. And what we'd love to do going forward is to actually try to disaggregate all these sources of uncertainty even further for more intuitive decision-making. And that's a segue that leads us into the ST-Parser replacement project. Now, please ignore this big wall of text. I'm not going to be going through it. This is just our one-pager to describe the project. What the parser system is, basically, it's a system that runs every 30 minutes, and it's just a way of doing a 7-day outlook, of a rolling 7-day outlook of system adequacy. So kind of things that it'll look at is looking at our supply and our demand mix, ensuring that our reserve levels are quite adequate, making sure we have system security and reliability sets met. And it's also a tool that participants can use to make informed market decisions like coordinating planned outages. The current parser system is pretty good. It's very effective, but it wasn't really built with the flexibility to handle new emerging technologies that are coming into the grid, like battery storage, VPPs, DERs, etc. So because of that, we're actually doing a really, really large project, and we're overhauling the entire parser system and putting in a replacement. I'm not going to talk about every single aspect of that, but 2 features that are relevant. One of them is that we are moving down from a top-down regional-based system to a full nodal network. So we are going to be solving and optimizing for the system and for our outlook right down to the bus or right down to the node. So that's going to allow for really more accurate system security information. And it's also going to allow us to make more targeted decisions because we know exactly where perhaps certain deficits may fall, where certain constraints and issues may come to place. The next feature that is relevant, what I'm going to be talking about today, is a piece of development that I'm working on uncertainty margins. So this is a way to actually take a look at our 7-day outlook ahead and actually try to adjust all our supply and demand forecasts to account for uncertainty. So to ensure that we're actually trying to account for all the different components and sources for uncertainty and bring that right down to the node. So I'm going to give a bit of an example just to demonstrate what that looks like. Before I do that, just a quick note. When I say uncertainty, what I'm actually referring to is the forecast error, or just the forecast minus the actual. And the way that we're using probabilistic forecast methods here is we're simply just taking the distribution of those errors or distribution of uncertainty and just trying to find probabilistic cut points or quantiles and making our kind of decision points on that. So let's go to this example. Imagine a really, really simple system here. So we have all our generation on the outer circles, we have our lines, and it connects straight to our buses or our nodes or our load points. Now, we have forecast for all of these components. We have all our generation forecasts, and we're actually doing a method for this project to disaggregate the load right down to the bus. So we're going to have a forecast right down to the bus for every single node in the system. So what that means is right now we got a forecast for all of this. So what we can do is we can put this straight into our optimizer, straight into our SCED, and we can solve it. And we can see, okay, great. Do we have system adequacy? Are there any deficits? Fantastic. But the next thing that we're going to do is we're going to do a new run type. We're going to take all of these forecasts that we have, and we're actually going to adjust them for uncertainty. So what that looks like, for every single bus, we are going to adjust the demand forecast by adding the corresponding uncertainty. So we're going to kind of say, what happens if there's additional uncertainty and extra load that we need to serve that we haven't accounted for in the forecast? So we're going to do that for every single bus. For every single VRE unit, we're going to adjust the forecast by subtracting the corresponding uncertainty. So just to see, is there a scenario where we have less supply availability because we have due to certain levels of uncertainty? And for our scheduled units, we don't get forecast, but we do in the maximum availability. So again, we're going to adjust those generation availability bids by subtracting for uncertainty again. Okay, so back to the system. Let's see what this looks like. First step we're going to do is we're going to calculate a top-down regional level of uncertainty margin for every single component. I'll come back to this in a moment just to explain why we use that. Next thing we do is we're going to take all our individual VRE units and adjust for uncertainty. We're going to take all our bids, adjust for uncertainty. And we're going to take all our demand forecasts right down to the bus, and again, adjust all of those for uncertainty. Now, next, to ensure that we're not double counting or rather over counting for uncertainty, we are going to scale all of those individual uncertainty margins so that they do not exceed the top-down regional level of uncertainty that we've just calculated in step one. That's just to kind of make sure that we stay in control of the uncertainty that we are kind of forecasting out. And that's it. We've got all our forecast components, which we had before. Now they're all just adjusted for uncertainty at an individual level. And great, we put that into our SCED, which is our optimizer, and we solve. And we do that a few times and for different run types and different kind of risk thresholds for uncertainty. So this is a bit of a paradigm shift. Instead of trying to say, let's set a new level of reserve, or let's try to set a reasonable level of reserve, instead, we're going to take a look at our current supply and demand mix, account them for uncertainty, and see, will the network still solve? And if there's any issues coming up, well, we're right down to the bus, right down to the node here, and we can be really, really targeted and specific and accurate in where those issues are going to fall place and take really informed decisions from there. So this is quite a significant undertaking. It's a really, really big, this is just one part of that. I think we're going to try to go live in 2026. So definitely watch the space and we'll see how we go with that. All right. Next thing I want to talk about is how we're managing increased risk from weather uncertainty. One thing that we often try to do is reconcile different weather outlooks and uncertainties. So we have about 4 different weather vendors coming in, giving us NWP feeds. And, you know, sometimes they're the same, sometimes they're different. Sometimes we can have temperature forecasts or a couple of degrees off. Sometimes we have a cool change or a breeze coming in, and some forecasts are saying it's a bit sooner, a bit later. And really, there's just a whole lot of uncertainty that's embedded in all these different outlooks for how the weather's going to play out. So we get really good visibility of all the different ways the weather's going to play out. But the question we often ask ourselves is, so what? What does this actually mean for us? So we've recently developed a weather scenario tool to address this. So this was a really, really interesting collaborative project that we've done with our National Bureau of Meteorology. they provide forecasts for all our key weather stations that we use. But under the hood, they also have all these different ensemble members running. So we've really actually engaged with them, and they've kind of tailored this product just for us. We're getting all those ensemble members, and they're doing their calculations and translating it into a weather station forecast, which looks exactly like the type of forecast that we're feeding into our models. So right now, we're getting our main weather forecast model, passing it through our machine learning model, and now comes our operational demand forecast, I should say. Now all we're going to do is just swap that feed with all these different scenarios and all these different ensemble feeds, pass them through, and then we get all these different outlooks of what the operational demand could be. So it's a very simple but also very novel method of actually translating what the operational impact is of every single weather scenario and outlook that we can do. And this is going to really help us to increase situational awareness and preparedness. So I'll give a very quick example. I've got a few minutes left. March 14th, New South Wales. This is the tail end of our summer. We had a pretty hot day. It was looking to be about 90 or so degrees Fahrenheit. But there was a bit of uncertainty. There was some uncertainty as to whether could the temperature be a few degrees higher. There were some indications that this really, really significant cool change that was going to come in and really like knock down the temperatures across the entire state. Well, it was likely going to come between 2 and 4 p.m. Well, that's a pretty wide range. And we had some scenarios saying sooner, some scenarios saying later, some vendors saying it was going to come way later in the afternoon and the evening. So again, so what? How do we actually reconcile all that? This is just one of our weather stations, our Bankstown station in New South Wales. It's just the temperature forecast. So this was our control forecast. It said that we were going to have a peak of about 90 or so degrees Fahrenheit, and there was going to be a cool change coming in about 2 p.m. But we're also getting all these other scenarios coming in now. We have a scenario in which the temperature gets higher and the cool change comes later. We're also getting in a scenario which cool change comes a bit earlier. In fact, we get well over a dozen scenarios now because we got this new feed for our National Bureau. And cool, we can kind of examine all these scenarios individually. We can wrap around this whole temperature band around that and just get a little bit of visibility as to where the temperatures could fall. Again, it's a bit of a so what. In case anyone is interested, temperature did go a bit higher, but there was a very, very sharp cool change that came in 1:30 p.m. So I was 30 minutes sooner than expected. Right, let's look at our demand side. So based on our control forecast, this was our control operational demand forecast. This is the main forecast that we publish. We publish this to the market. We send this to the control room. We give this to our participants, our operational planning. Basically, all our decisions are saying this is our best looking forecast ahead. But we also have all these other weather scenarios, and we can pump that through our tool and get a whole heap of different operational demands and how each individual scenario actually has different sensitivity and how they can actually impact the change and load for the day. Now, again, we can kind of look at all these scenarios individually, which is really good, or we can just kind of wrap a temperature, a band around that. Now, I'm not suggesting that we need to plan for every single one of these scenarios or try to like accommodate for every single, for this entire range. But what this does is it gives us so much more situational awareness and it empowers us with so much more situational preparedness that it really helps us make really much more informed decision-making, and it really enables the control room and others to really kind of get a really better idea of how, say, tomorrow is going to plan out. Sorry, I did forget to say this was all our day ahead forecast. Again, we know that cool change came in sooner, and the impact of that was that we had about 500 to 600 megawatts of load actually coming in below our day ahead operational demand forecast. So that's really a really significant deviation for us, but it was actually really well captured by this range. We had just developed this tool kind of a week prior, so this was a big use case, so it was really fantastic that we could use it. And yeah, it just introduced a whole bunch of different levers and mechanisms and awareness that we could kind of leverage in a day ahead format for such a tricky, uncertain kind of day. Lots of different improvements and next steps. This is a very, very, I guess, new tool that we've operationalized. I think one of the key things that I'll just highlight here before I wrap up is that probably the middle point likelihoods is something that we really want to introduce. Right now, each of the ensembles are just being fed in, and they, I guess, have equal likelihood, just the way that we're seeing it. But if we could actually work in a way that we could have probabilities or likelihoods actually attached to every one of these scenarios, it just means communicating to the control room and communicating risk and kind of bringing up that kind of language of communication will just be a lot more effective. So I am over time and I'll wrap up. Thank you.
Fine questions for Andrew? Okay. Certainly, we'll have a time at the end for discussion and additional questions. So for the panel, for the full panel. So we'll move into a discussion. Jeff Baskin from SPP. He is a meteorologist, a technical analyst, and he'll be discussing using probabilistic forecasting at SPP.
I'm just untangling this a little bit. Well, good afternoon, everybody. Y'all still awake this afternoon? All right. Okay. I got some thumbs up and some heads down. Okay. So that's good. All right. So I'm Jeff Baskin. I am with Southwest Power Pool. I work in operations with the uncertainty response team. And so what our team does is we evaluate the forecast and then we figure out what could go wrong with this forecast. And as it turns out, a lot can go wrong with the forecast for several reasons. So this is what we're talking about today. What we do in the uncertainty response team to produce probabilistic forecasts, both using historical data and also getting into fancy ensemble data too. So here's what we do, and here's why we exist. We have lots of growing uncertainty in the energy field with increased renewables, temperature, weather uncertainty, and aging infrastructure, especially some of those older traditional power plants. So here's what we do. We work in the next 7-day range. We're on a staff, we're on call 24/7. We're looking at weather conditions, load levels, wind forecasts, generator outages. We develop mitigation plans ahead of time. That includes long lead unit commitments. If we see something, a potential issue down the road, but there's a unit that has maybe a 5 or 6 day starting time, we may make a recommendation. Let's get that up and running and get it ready while we still can. We also recommend system advisories, such as a resource advisory if we're looking tight, potentially conservative operations. We also recommend weather advisories as well. And we also work with outage scheduling to coordinate outage denials and rescheduling when necessary. And we're doing this pretty much on the span of the next 7 days. The assessments are done all time horizons out through 7 days in an hourly factor. The main factors we're looking at: load, wind, and resource error. And what we do is we apply the available online and offline capacity over each horizon and look at that error. Again, we fall in the different time horizons of these forecasts and analysis. We are in the operating day -7 to the operating day time, although we do work with the generation assessment as well. So this is what we look at on a daily basis. This is what our team looks like. We look at net load. What's our net obligation compared to our available capacity? What can we serve? And we look at the different probability levels here, where the black line is actually 95% and that orange line is 99.5%. And the bottom line, that's the base forecast, that light blue line. So when we see that some of those probability bands are going over available capacity, that's when we start taking action. And again, that can include actions such as rescheduling outages, making some of those long lead commitments. We'll run scaled forecasts to see what additional generators may need to come online, what additional problems that could result in, such as congestion issues. So we look at the scaled forecast, which includes the load uncertainty and also the resource uncertainty, as well as the wind. So we break down the load forecast uncertainty into the underlying load uncertainty and the resource. That's what's put into that overall load uncertainty. So we're looking at these three factors, and it helps us identify what risk is most prominent. A lot of times it's going to be a combination, but sometimes you might see this is mainly a risk with the downside risk on wind. This is load driven. This may be resource driven because of high outages. And we combine this forecast, and this is something that we send out to pretty much everybody in our entire company. This is a high risk scenario report. It shows what percentage of our total available capacity is going to be used for each probability value. So your 50th, that's your forecast. Now in this case, you know, we look good for a couple of days, and then Monday, January 15th, looks like, whoa, wait a minute, that we're gonna serve to serve our obligation, we're going to need every bit of capacity to maintain our reserves and not getting into our reliability units. But you can see that as you go up in those p-values, then those percentages start getting higher than the available capacity. So then you need to do something to either get your load down, which isn't really easy to do, or you need to get some additional generation online. So that's where you have to take action. In this case, we would issue an advisory, either resource advisory, conservative operations, to try to get some of those outages rescheduled and get everything online as possible. So here's our process for air forecasting, and it really starts with the weather because that's the primary driver in uncertainty. So what we do is we take a look at a lot of our weather stations, and we're going to look for temperature anomalies, either cold anomalies or warm anomalies. And in this case, you can see the red outline temperatures. That shows where temperatures are likely to be unseasonably warm in the top 10 percentile of say high temperatures compared to average. And this is all done in-house. This forecast is done in-house and delivered that way. So we use those temperatures to determine not only what our forecast load is going to be, but the potential air for that forecast load as well. And you can see that in extreme cold temperatures, they're a lot more subject to large airs, as well as also hot temperatures. In the middle, that's where you have your least risky temperatures. And so this is what the load air forecast might look like, where that load air is going to go up with time, as you would expect. And then we can take a look, we can add that to the base forecast and get an idea of what is the potential load for each probability. And we also do this with the wind forecast, except we're not worried about going over, we're worried about going under. So what is the probability that the wind is going to be at least to a certain level? And you can see that that confidence, that range, really depends on the actual wind amount that's forecast. When wind is forecast to be low, well, the potential air is not as high. It's really right in those middle capacity factors where a small change in wind can mean a large change in power output. And that, in terms of air, is the riskiest scenario. And then also a resource forecast air. So we have a schedule, what's scheduled to be an outage, but things do change. Sometimes outages get extended, we get forced outages, we get unit trips, and this is what we try to account for in each of these air forecasts. And we use this, we combine these all to get our net air forecast. And what we do is since not all of these airs work independently of each other, we want to look at them holistically. The airs are multiplied by a coincidence factor, which is determined by looking at the historical data to get a more holistic view of what that air is going to look like. And here's an example of air increasing over time, but you can see that there are some time periods that are certainly more risky than others, where that spread is a lot higher. And so those are the time periods that we're going to look at. Now you might be wondering, well, how does this do? Does this actually work? And yes, it does. So here's an example of our actual load compared to our 99th percentile load forecast. Let me go back there. And these red lines here indicate where we actually have exceeded that value. And that does happen occasionally. You can see back in mid-January, I don't know if you can see my little mouse pointer there, but that's actually as Winter Storm Jerry came in. And there were some load misses there because this is based on a 5-day forecast. the cold air came in a little bit sooner than what was predicted 5 days out. So there were some load misses there. And then we actually see that happen on a couple of occasions as cold air comes in later on during the winter. That happens a couple more times. So it helps us to identify when are we seeing those airs and nailing down some reasons as to why we may be looking at those airs. Here's another example using wind forecasts. When the wind forecast drops below the 99th percentile wind forecast. And again, that does happen, but at a rate that you would about expect to see. So we put this all together, and this is the net air forecast. This is, if you look at that 99th percentile forecast and you compare that to what actually happens, most of the time, of course, you're going to over forecast. That's what you'd expect because you're trying to get that 99%. But there are some times where you do actually violate, you go over that. And again, one of those time periods was Winter Storm Jerry due to both load and also resource error, a lot of outages that came in quickly. And there's, as we got into a quieter pattern, we saw very few in the way of those violations. So, looking at breaking them down, how often we get those violations, at first it looks like when we look at the load air, maybe we're not being conservative enough. But again, we're looking at a coincidence error. So not our coincident error, not the error just based on load. So we'd expect that looking at any of these individually, the errors probably wouldn't be conservative enough. And you see the same trend with the wind air validation. But when we look at the net air validation, it's actually very, very close. The black line indicates pretty much a perfect scenario where you're 70, for P75, you're violating 25% of the time. For P90, you're violating 10% of the time. So it's for the most part on each of the different time horizons, very, very close to what we expect. So it's not perfect, but it does overall give us a really good idea of what kind of errors we can expect. But we're also moving into the world of ensemble forecasts. One of the advantages is you can actually take a look at the forecast and the underlying forecast uncertainty into your uncertainty forecast, which using historical data doesn't really do that. So there's a couple ways to do that. One is looking at wind power forecast ensembles. This is an ensemble forecast for ECMWF wind power output for our fleet. This is an aggregate forecast. And you can see that, the forecasts after a few days really don't look that good. It's just, well, okay, pretty much anything can happen. Anywhere between 2,000 and 20,000 megawatts of wind. Great, thank you. Okay. I think I could have told you that without this fancy graph. Okay, but it does give you an idea of, especially in the shorter term, of when are those wind ramps more possible, when you might see those big wind ramps and what the air may be at those times. And you can see that at sometimes it's more confident than others, and it's not a linear relationship. As you go farther out, it gets less confident, as there may be different weather scenarios, such as the front coming through, or differences in the models with high pressure building in, that may affect when something happens. So that's and you may get higher air during those time periods. Also, looking at temperature, we can look at weather model ensembles. This is an example for one of our weather stations. This is looking at the GFS ensemble. This is all 30 of them, so you can get a look at the range. And, if we had a particularly risky scenario, one of the things that could be done is you could go and look through these different charts for different weather stations and identify, well, where is this uncertainty? We have, it's not evenly distributed where we're uncertain everywhere. Some of our weather stations may be pretty good as far as consistency within the ensembles, and some there may be a very large spread depending on the weather situation. So once you have your different wind forecast scenarios, you have your different temperatures, you have your different weather scenarios, you can build out load ensemble forecast. This is an example. This is actually based on a European weather forecast, where you're taking the different forecasts, you're running them through the same model, just with different weather inputs, and you're coming out with a different load forecast. And that gives you your range. So you can take that range and you can convert that into probabilities, what we were looking at before with our historical probabilities, where that white line is 99.5%. The black line is your, and the bottom is your base forecast. And you can see, as you'd expect, that spread gets higher, especially as you go farther out at time. And of course, your greatest uncertainty is typically right near those peak periods, right where you're most concerned about. So we're comparing the historical error compared to the ensemble error, you wind up seeing fairly similar results near peak. The timing is a little bit different. The ensemble's errors are usually higher right during the forecast peak. Historical error looks a little bit more at those, takes into account those ramps a little bit more, and that's why you see those double peaks starting around days 4, 5, and 6. And you have lower errors at night, which you would expect. And I've looked at this a few times, and generally it's pretty similar. But you can look at this, and if you see that the ensemble forecast error is much higher than your historical error, then that's a good indication that this is a riskier time period than normal. Something is going on, and you need to look at that more. If you see that the ensemble error is much lower than your historical error, then you can look at that as being an above average confidence situation. So you may not have to be as conservative going into your forecast as you would just based on historical error. So looking at summarizing it up, as far as the ensemble error advantages, it can be used in conjunction with historical error to identify the time horizons of above or below average confidence. And it captures the actual uncertainty based on the spread of the underlying inputs, such as temperature, wind, cloud cover. And also, obviously, you can do it without having any historical data whatsoever. So if for some reason you're building out some new infrastructure, you don't have good historical data, you can use an ensemble forecast to almost simulate your historical errors. So that's another one of the big advantages. And that's all I got. And I will take some questions, I guess, later on.
Any clarifying questions for Jeff? No, I think they're all gonna come at the end, I think.
Okay.
So please take notes and jot down your questions, and we'll have a pretty robust conversation at the tail end of after the panelists are completed. So the next presentation's coming from Lysha, Matsunobu, and thank you. Okay, she is from CAISO, and they are implementing a number of interesting, innovative probabilistic solutions or solutions to probabilistic problems, and we'll look forward to hear what she has to say. Thank you.
All right, thank you, Tim. Yes, so Lysha Matsunobu. I am a power systems forecaster specialist at the California ISO. I work on the short-term forecasting team. A lot of other team members contributed to the work that I'm going to be presenting today. So special thank you to Tobias Steckel, Hong Shou, Rebecca Webb, and Amber Motley. So I am coming here. I'm going to tell you the takeaway you should take away up front. The message I'm trying to communicate here is probabilistic forecasts help us manage uncertainty. Adapting for conditions helps us balance cost with risk. So one of our lessons learned recently of implementing uncertainty products is that there's always this balance to strike. You can say with high confidence that the minimum generation of solar is 0 megawatts, but then that doesn't really help you. And you don't want to carry too much requirement when you're uncertain, but you want to have enough requirement to cover your uncertainty. So there's this balance you need to strike, and your risk appetite can change day to day based on many other conditions. So how not, as David Larson said in the opening session yesterday, it's not so much a problem of how do we create probabilistic forecasts, it's how do we interpret them and then apply them. So I'll do zoom out now to the California ISO. We are one of 9 ISO RTOs in North America. The big number to highlight here to give a reference for our system size, our net load record peak demand was 52,000 megawatts in September 2022. And CAISO also manages the Western Energy Imbalance Market, for which we have 22 participating entities, led to many climate and economic benefits there. More relevant to this presentation is the significant amount of renewables in our system. Our solar peak, we've been hitting a couple records recently. On May 13th, we hit a solar peak just below 19 gigawatts of solar. Our wind peak is 6.4, almost 6.5 gigawatts. And in April, we had a new record peak of renewables serving load of 117%. Renewables there is aligned with the California RPS standards. So renewables is solar, wind, biomass, biogas, and small hydro. So we're already seeing that renewables have a major footprint in our net load profiles. In the bottom, these stats here are now for solar, wind. So for the resources, the variable energy resources that we forecast, we have 529 solar wind resources. That is a capacity of 27,872 megawatts and growing. And then our estimates for behind the meter solar capacity is 16.2 gigawatts. So again, system load of 52 gigawatts. These are very large numbers of renewables compared to our load. So these big drivers of uncertainty, solar, wind, because they're variable, but also we're seeing load have a lot more associated uncertainty that we don't necessarily have as much visibility into. Electric vehicle charging, rooftop solar, behind the meter batteries, building electrification, many different drivers of load uncertainty. So I'm showing on the bottom left with stable forecast progression, but when your load starts to have all these lumps and bumps to them, the associated forecast error will grow. Repeating Andrew's point, we're not going to forecast our way out of uncertainty. So we need to find a way to handle this. And CAISO has 3 uncertainty products where we use probabilistic forecasts. Moving from furthest out horizon to real time, we have the imbalance reserve, which handles uncertainty from the day ahead to 15 to real time markets. A flexible RAM product, which forecasts uncertainty in the real time market timeframe, and then regulation, which handles from real time to actual. For us, when we say uncertainty, we're defining that as a forecast to forecast error or difference. So not forecast to actuals. It is in my day ahead forecast at an hourly granularity. Once I break that down to a 15-minute interval forecast, there's going to be some inevitable error. But in addition to, the error that's coming from different weather conditions or variable renewables changing, there are how we define our uncertainty definitions and train. Okay, so for this presentation, I'm going to be focusing on that furthest out horizon one, imbalance reserve. And I am saying imbalance reserve, but I'm going to switch to now RUC adjustments. RUC adjustments are a non-market action that operators can take to ensure there is enough capacity to meet the uncertainty that will arise between the day ahead and real-time market. Imbalance reserve is the uncertainty product that will eventually be rolled out with DAME in 2026. And right now, our RUC adjustments mimic the method that the imbalance reserve will eventually use to calculate uncertainties. The key difference here being that the RUC adjustments are non-market actions, whereas imbalance reserve will eventually be a market product. Let me skip to the next slide first and then come back to this one, because I think this is the visual representation of the next slide. This is a timeline of where we've seen RUC adjustments and this IBR, like day ahead to real time uncertainty, evolve over time. It used to be that in the summer 22, winter 22 timeframe, we were just taking an aggregate of uncertainties. So we were saying, let's take our lowest confidence load, let's take our lowest confidence solar and wind forecasts, and then lowest confidence bands for load, add them all together, and this gives us our bands at net load. But taking 3 lowest confidence bands, then leads to an extremely low confidence band, or you're just aggregating and overcompensating, over procuring capacity. So we adjusted that approach, especially with the design of IBR to in July 1st of 2023, we're now implementing an imbalance reserve like uncertainty product that more smartly sort of accounts for that coincident uncertainty that you might see. It's called mosaic method. It uses quantile regression in a two-step process where you first sort of train on your historical load, wind, solar forecast uncertainties, combine them into a mosaic variable. So there's now a second step where you do another regression of net load uncertainty compared to your mosaic variable. So that helps handle any coincident or correlation uncertainties into your three separate products. So that method was implemented in July, and then that method has a target percentile uncertainty coverage of 97.5. But we found that that led to very high requirement calculations, so we adjusted. So maybe we don't always want to procure at the P 97.5. We need to have other options. So December, we implemented options to provide those numbers at other percentiles. And then in May, we need to even tune this more to provide more options for the operators to be able to adjust to the current conditions. So a lot of tuning going on recently to help make sure that these probabilistic forecasts are actually responding to conditions in the right way. So now I'm going to go back to this slide, which is we're looking at RUC adjustments, the distribution of and magnitude of RUC adjustments over the 24 hours of the day, and then summarized by year. So 2017, 2018, you see that RUC adjustments were fairly small, pretty consistent in terms of magnitude across the day. You see them more in the daytime. But then the magnitude and frequency of RUC adjustments starts to grow. This is associated with the growth of these uncertainty drivers of load, wind, and solar. And in 2021, 22, that's where we started implementing those additive aggregate uncertainties. And you see very large RUC adjustments being procured. That led to that refining and tuning, so that now we're in this 2024 timeframe. We still have the ability to do these RUC adjustments and to learn from historical uncertainties, and then be able to predict for future conditions. Okay. So what does that look like in terms of the daily average RUC adjustments? You can see at the 97.5th percentile, even though the amount of requirements procured per day does change, we're using that forward-looking net load, we're using the forward-looking solar, wind, and load forecasts to inform these requirement estimates. But at the 97.5th percentile, very consistently, you have very high average requirements of capacity that will be procured. On December 21st, 2023, at this dash line, we've now implemented these adjustments, so you can now look at your requirements at the 50th percentile, 75th percentile, 97.5th percentile, and use other conditions to inform, your risk tolerance and which percentile you choose. So the full list of conditions that operators are encouraged to consider is outlined in Operating Procedure 1210. Not going to go through any of that full wording there, but some highlights of what is considered would be weather, temperature risk, west-wide grid impacts. If X number of regions are hitting historical records of highs or lows for temperature, then we would probably opt for more conservative probabilities. And then your operational RA supply and expected outages, et cetera, compared to expected load. So this gives the operators flexibility to respond to conditions, and where I'm going to highlight the one outlier you see past the dash line in this example case where we had a cold event come through and affect the WAM in January. January 13th is the first day, and then we're looking at a 3-day RUC adjustment compared to uncertainty. As I said in the beginning, our uncertainty is defined as a forecast to forecast error. So net load, 15-minute ahead, or FMM, 15-minute market forecasts, and then compared to your net load day ahead, which is at an hourly granularity forecast. Take those differences, takes the max per interval. So you're already embedding some conservativeness to this definition of uncertainty. And then you're aiming to, cover your 97.5th or 75th or 50th percentile of those uncertainty values per hour. So the gray bars on this plot are the realized uncertainty at that interval level, 15 minutes. The red bars highlight that max uncertainty per hour. So the requirements are really meant to cover at whatever the target percentile is, cover those red bars. So on the first day, we saw west-wide grid impacts for cold conditions, went with a 97.5th percentile, saw that lead was not ultimately needed. We over procured capacity in that sense. So, and we had more appetite for risk later on. Not that it was extremely risky, but saw that we were probably playing it too safe in the beginning. So opted for the 75th percentile target in the following days. But this is a very real-time operational decision that has to be made. And we try to put in some programmatic rules or default recommendations, but ultimately it is up to the operators to make these choices, but we can provide them the options at these different target percentiles. So that brings us to the summary. Hopefully I've gotten the point across that adapting for conditions helps us balance cost with risk. Again, it's hard to answer the question of what is the exact formula for risk appetite versus cost, and what is the optimal solution here of how to interpret probabilistic forecasts. It's really good to have all that information, but creating a step-by-step procedure of how to then ingest it is an ongoing process for us. In terms of next steps, we have implemented a couple changes to FRP. We are still tuning our ability to do probabilistic forecasts correctly and ensure that they produce the percentile coverages that we're targeting. A lot of that comes with sample tuning. So those are some changes that we've put into place and communicated out. And then just overall, there are a lot of areas of tuning to continue exploring. Data quality tracking is really important in this space when you're trying to predict at the tails of a distribution. Your sample heavily impacts those estimates. So constantly trying to figure out what data quality measures to put in place, how do we track it, and then also recommendations for conditional triggers for our operators and how to provide some methodology to interpreting, your P90 or P97.5, et cetera. So that is it for me today. Look forward to questions. Thank you.
Great, thank you so much. Any clarifying questions from the floor, from the audience? Okay, great. All right, we'll move to the MISO. We're moving off from the coast, moving towards central CONUS. I first heard that for the expression yesterday, so I'm definitely a newbie at this thing. Wang is the manager of operation risk assessment for MISO, and she's going to talk a little bit about the MISO uncertainty tool, which is groundbreaking. So looking forward to hearing the discussion.
All right, thank you. Can you hear me? All right, good afternoon, everyone. My name is Wang with Operations Risk Asset Management at MISO. So go to the next slide. Oh, I need control here? Okay, sorry.
Or you can use the clicker, right?
Okay. So want to talk about MISO's uncertainty management efforts here. The rapid fleet transition is really driving a new risk profile for both the market and grid operations. So as we know, historically, going into the operating day, we have a good handle on what to expect for the load. And our largest uncertainty is the loss of largest contingency, which we have operating reserve to cover. But now everything's changing. So at MISO now we have over 30 gig of wind generation, and then our solar generation just passed 6 gig. So although together the in-service capacity of the wind and solar is still about 40 gig, less than a third of our total installed capacity, but we do see on those warm spring days, our wind and solar serves more than 40% of our load. And very interestingly, on those extreme heat days like last August, when you see all-time peak type of load like 127 gig, we only have wind generating a few percent of serving a few percent of a load. So this really highlights the variability and uncertainty we are managing, and not only wind and solar for load. As we talk a lot today, the electrification is really driving a new risk load profile, whether that's behind meter solar, which we don't have a lot of visibility, and data centers, and even the non-conformal industrial load. So on top of the normally discussed load wind solar, the thermal generation can be a factor of uncertainty too, as we see during those extreme cold weather. There's uncertainty of the availability of generation resource, either due to the fuel scarcity or due to those extreme temperatures. And also, as a MISO, we see it in the middle of a lot of other RTOs, which is quite fortunate. But meanwhile, another large uncertainty factor is the imports, exports. We can go all the way from over 10 gig of net imports on some days to the a few gig of net exports on the other days. And meanwhile, as we really look forward to the MTAP to expand our transmission capacity, now we manage transmission congestion every day, which really can trap some of the generation capacity seemingly available, but really not accessible because of congestion. So all in all, as we can see, the reliability now is not really just meet the projected load obligation, but manage uncertainties. So our efforts of uncertainty management really are threefolded. First, we start with characterizing the individual risks. We try to establish probabilistic forecast for things that we traditionally forecast, like load, wind, solar. But meanwhile, we try to develop advanced analytics to capture those unknowns or those things that we historically don't forecast, like the generation uncertainty or the imports, exports uncertainty, or even the transmission uncertainty. And then next one is to integrate these risks into the operations planning and the situational awareness to provide control room, the centralized visualization of those uncertainties, but also include those in our operations planning unit commitment process. So mainly really try to quantify and predict net uncertainty, and then utilize dynamic reserve requirements to really obtain the needed attributes to manage uncertainties with appropriate market signals. So our uncertainty platform really hosts our risk efforts, aiming to transform the deterministic way of we traditionally manage the grid and markets to more probabilistic way. So this is a cloud-based platform. We just finished up the solution architecture design, and we'll move forward to the building phase later this year, especially thanks to the DOE grant with the Optima fund. So what this uncertainty platform does is really on the left, it digests the probabilistic information from load, wind, solar, and also the advanced analytics with the quantified risk of those generation fuel availability, net schedule interchange, or the transmission risk. And then on the right-hand side, it tried to enable the probabilistic operations planning and also the dynamic reserves for the market and commitment process. So in the center, that's the core of the platform. It really does two key applications. One is the centralized visualization of the holistic risk profile. So we have more kind of understanding going into not only the next day, but the days ahead, what to expect, what risks are in the horizon, so that we can proactively plan for it. And also the advanced analytics for this platform, really trying to derive the key operating scenarios that we should plan for in our operations planning process, and also dynamically setting the reserve requirements to obtain the needed attributes to manage the uncertainties. So next, we'll take a closer look of each of these key applications. First, look at the left-hand side, really look at our efforts to establish probabilistic forecast and risk analytics to quantify the individual uncertainty. For load, similar efforts to what Andrew talked about, we just implement in production weather scenario-based load forecasting. What this one does is, instead of today, we produce a deterministic load forecast. We derive multiple load forecasting scenarios from 8 high-performing numerical weather prediction models. So on the right-hand side, this shows kind of our holistic dashboard of visualization of these load forecast scenarios. The top right is those scenarios, load scenarios along with our primary forecast. So what immediate term, these multiple load forecast scenarios will help us to quantify the uncertainty associated with the load forecasting. For example, this summer, what we really look forward to is, let's say if we go to a very hot day and there might be a storm coming in, if there's a high resolution model is capturing that storm better, that can really help us quantify, or maybe there's 3 gig of downside risk. That will really build the confidence for unit commitment. Let's hold on these short lead units until we get close. So another efforts with this is to really try to develop advanced analytics to dynamically optimize the weighting of these multiple scenarios to improve the forecast. So that is the one we are collaborating with our R&D and also looking for thought partners to work on this like ensemble analytics technique. Similar efforts has been done with our wind and solar forecasting. We are partnering with our vendor to really get multiple numerical weather prediction model-based wind and solar forecast scenarios, as well as some of those for wind, like extreme weather scenarios, like icing scenarios, to help to assess the uncertainty, but also try to improve the forecast. Lower, further down, marching down is really the analytics. Use a few examples. First one is our analytics to really assess the generation availability risk. So one of the efforts, if we overlay our gas fleet on top of our gas pipelines, and then we have staff closely monitoring, especially during the extreme winter, like what are the gas pipelines that might have those critical notice. From there, we will identify which units, how many gigawatt might be at risk, and then we can plan accordingly. And similarly, the NERC has been really kind of driving the industry to prepare for those extreme weather, cold weather events. So with the winterization support, we got good data in terms of the cold temperature cutoff for a generator, either fail to start or fail to run. So we utilize that data over our temperature forecast, so that we can see which unit at what location, how many megawatt might be at risk to fail to start, so that we can assess that risk, considering that in our operations planning and unit commitment process, and even initiate the coordination with market participants. For the net schedule interchange, the imports, exports, our data scientists did is try to cluster those imports, net imports we used to get based on the neighbor condition, like shown here is the PJM's load condition. So from there, based on our monitors of our neighbor's condition, we can get an understanding of this type of condition, what type of net interchange we should expect. Don't have the transmission risk efforts here. This is something we are partnering with NREL to really try to develop advanced analytics to and optimization to assess the transmission side of the risk as a part of our DOE grant. Moving next is one of the key examples of the advanced analytics that we're going to build into this uncertainty platform, which is to quantify and predict net uncertainty. So based on this capability, we actually operationalized the dynamic requirements for our short-term reserve and our next day reserve margin threshold since the beginning of the year. So MISO has a portfolio of different market products for different purpose. On top of this short-term reserve and next day reserve margin, we actually also just teed up to our stakeholder community to look at the dynamic RAM capability product requirement and also the regulation requirement based on the changing risk profile. And also for the next day reserve margin threshold, we don't have a market product yet. This is currently done through an operating process, but we do have our attribute roadmap aiming to develop a day ahead uncertainty product, which this will fit perfectly to set the requirement for that product. So for the dynamic reserve, there are three key components. First one is to quantify the net uncertainty. We'll talk about how do we define net uncertainty in the next slide. But from here, so if you see on the right-hand side, that's the quantification. What we do is look at the historical distribution of our 30-minute through our net uncertainty, and then define our high, medium, and low uncertainty covering the 90, 97, and 99 percentile. And then the next key component is the net uncertainty prediction, which is a machine learning model, the gradient boost model, as well as a few other models running in parallel, try to predict for the next operation. Are we going to expect high uncertainty, medium uncertainty, or low uncertainty? From there, we set our requirement based on the predicted uncertainty. And we do this for system-wide, but also for the sub-regional level, so that we can clear the reserve at the right place. Then we have a operating procedure to standardize this process. And then once we build into uncertainty platform, it will be fully automated. And the lower right shows the performance of our machine learning model to predict uncertainty. Since this model was established last July, the performance has been much improved, as you can see from the figure, including the past winter storm. We'll talk a little bit further. So here is the key point, how we define the net uncertainty model. It really tries to look at the holistic risk profile. As we know, traditionally, we look at the net uncertainty by aggregating the individual uncertainties and make assumption of their correlations, which we all know it's really hard to make that assumption. And one key step forward is with the E3 model that Ernie presented in this forum a few years ago, is really trying to directly look at the net load forecast error assembled from the load wind solar. I know a few colleagues already also working on that. So from there, another further step we took is really leverage our big data asset at MISO. We not only look at the wind load solar, but also try to capture the generation de-risk forced outages, those generation availability uncertainty, and also our net schedule interchange uncertainty. So that's kind of how we define the net uncertainty based off kind of like our risk profile. And then this one shows how this model, dynamic reserve model, verified during the past winter storm. I just realized different article called a different name. Unlike Yuri and Elliot, you have one name, but we call it winter storm Heather. It's really last winter. So this model successfully flagged high risk several days ahead, actually, particularly for the next day, allow us to set the high STR requirement and our next day threshold to procure additional reserve, prepare for this. So the model really kind of like look at the projected weather conditions, and then the machine learning automatically identify what are the historically experienced net uncertainty in these similar conditions. And then that's very like high uncertainty. So this really allowed us to pre-position, especially with the short-term reserve through the market. And as we all know, those winter storm is one of the best we've ever experienced. There's no escalation to any emergency operating procedures, but because of the joint efforts of the RTO and also our members collectively actually prepare for this. So the quantifying and predicting net uncertainty is one part of the important part of the equation. Also want to see like another important aspect is also try to have the situational awareness of how much reserve margin we have to manage this uncertainty. So then will further inform whether I'm looking at the risk to escalate to these emergency risk procedures or not. So we have this capacity sufficiency analysis tool. It provides the operating reserve margin outlook dynamically every 15 minutes up to 7 days for our system-wide and each region. So, and also this tool allow the scenario analysis capability so that we can access whether we have enough reserve margin to manage our projected load obligation, but also the uncertainties. This has been extremely important as we look at the extreme weather events, so then we can identify up to 7 days ahead whether we are at risk to escalate those emergency resource or procedures. and also allow us to proactively communicate with our members to coordinate and prepare for those extreme conditions to mitigate the risk together. And also another key development recently is building this net ramp concept. So historically, we look at the capacity, whether we have enough to meet the obligation. But as we all know, as we have more intermittent, faster ramping resources, the ramping or the flexibility also matters. So we build the visualization of what are the net ramp, which is a net of load, wind, and our import and exports. So we also provide this through our website to our members. So I think this is kind of like the overall updates. And from here, just one note for our uncertainty platform, we do aim to look at the potentially provide external access to our members so that not only MISO and our control center, but also external members can also have this situational awareness of what's upcoming in terms of the uncertainty. Yeah. All right.
Thank you, Congcong. Any clarifying questions? All right, we're consistent. We move now to Texas. Riaz Khan from ERCOT. I guess according to Charlie, ERCOT or Texas may actually be a foreign country. I'm not sure about that, but Riaz is a senior operations engineer with ERCOT. He actually is a former employee of mine, so worked for me at New York ISO. So take that for what it is. He is going to be speaking on the use of probabilistic forecasts in the operational risk assessment at ERCOT. So please.
Thank you, Tim. So yeah, I must admit first that my manager Luke Butler was initially invited for this talk, but he had some other plans and couldn't make it. So here's a replacement to frustrate you for the last 15 minutes of the day. So, right. So with that, I will go to my first slide. So when we talk about electricity, there are really two salient parts, right? Supply and demand. So here in this slide, what we're trying to show here is that on the left-hand side, the supply, and how it stands as of 2024, and how it's going to be in 2027, how it's projected to be in 2027. And the right-hand side, how the load is, changing. So if you look at the left-hand side, so if you look at, we have wind, solar, storage, and gas, what do we have in 2024, and what we anticipate to have by 2027. So two main points are here. That's wind and gas. They're not really changing much in these 3 years. But if you look at solar and storage, they are making significant growth in the next 3 years. So in summary, if you look at the bottom left, total transmission connected inverter-based resources, which encompass wind, solar, and storage, could exceed 81 gigawatt in 2024 and 124 gigawatt in 2027. So to put that in a context, so ERCOT's current peak load is 85 gigawatt and a change, which was set in August of 2023. Now on the right-hand side, you can see that there's a lot of bullets words. So I'm not going to go through all these things. So the main idea here is that demand is also changing due to population growth, economic growth, and electrification, and oil and gas load growth, and large flexible loads as well. So we're seeing changes in every part of the electric system, so supply and demand. Now, how does that work in our, so how can we relate to this theme that, probabilistic forecast? So we have seen the, previous slide that, both landscape is changing in the demand side and the, supply side. So with that, there is more uncertainties associated with that. So there's a need that we need to shift to a probabilistic approach to assess the operational risk. So currently we're working on a project that that is aiming to do that. So so we're trying to bring all the uncertainties from all the components like load, solar, and wind, and how we can use that, to assess the operational risks in terms of probability of, in the net load space. So the main idea is like, we have uncertainties from all three components and how we can, filter that through an engine to come up with a, distribution in the net load space. So yeah, so right now, this is in a prototyping stage, and we're aiming to test this, in the summer of 2024. And our long-term goal is to, implement that in our, production environment with appropriate, control and IT support. And in future, we look forward to incorporating other components of uncertainty like, batteries and price responsiveness and etc. Right. So, so as any standard process, this CAT project, we're calling it CAT, Capacity Availability Tool. In short, we're calling it CAT. So it has input, process, and output. So in the input side, we really have some hourly data. So we have hourly COP data, hourly load forecast data, hourly solar forecast data, and hourly wind forecast data. And for future consideration, that's not currently being used, the energy storage and price responsiveness. So for the load forecast, hourly forecast, and wind forecast, we're really bringing the distribution, not just a point forecast, but we are bringing the distribution for all three components. Now, the process we're doing, like, we're creating a band around all the forecasts, so load, solar, and wind. And we are, combining the forecast with our history, like what could be the error pattern, and we're going to combine that using a Monte Carlo simulation. So yeah, from all those simulations, we're trying to capture the net load. So for each Monte Carlo draw, we're calculating the net load, which is defined as total load. That's what you call for the native load. So total load minus solar and the wind. So we're deriving a net load for each, Monte Carlo sample. And that gives you a distribution for the net load for 168 hours or 7 days. That's the, window that we are trying to assess the operational risk for. And then, yeah, we're determining the forecast capacity margin distribution from the COP data and the Monte Carlo output. So the output space, what we're trying to, get from the Monte Carlo engine is that, event of occurrence, what is the probability that the capacity margin will go below a certain threshold? Like, for example, what's the probability that hour ending 3 tomorrow, the capacity margin will be below 5 gigawatt and so on. So, and some statistics, the forecast capacity margin, min, max, you name it. So these are just informational purposes. All right, so in this slide, we're trying to show the inputs. Some of the inputs, we have other set of inputs that's coming from the history. So we really are showing here the three components that, we're currently using for this tool: solar, wind, and load. So you're looking at three things, but it really comes with, like, not just the point forecast, but also the distribution. So on the top, you can see solar and wind. So we, as an ERCOT, we don't generate, as of now, we don't generate our own forecast for solar and wind. We have vendors that, provide us with the forecast, and they also provide, 2 points, like, P50 and P20, so 20th percentile and 50th percentile. So from those forecasts, we can create a distribution around the P50, and we can create the band. And for the load side, that's in-house product, and we just, create the point forecast, and we look at the history. We can bring the, associated error, and we can, put a band around it, like, we are creating the distribution on our own. So yeah, so we have the solar forecast distribution for 168 hours from the time of that, running on that engine. We have the same from the wind, and we have same from the load. Now we are, like, as described in the previous slide, that, we're combining all this forecast in our Monte Carlo simulation. But the thing is that, like, how can we combine that? Like, if we are talking about, like 5th percentile, we cannot just take the P5 from the solar, P5 from the wind, and P5 from the load. Probably that's, that would be overstating. So we're looking at the history, and we are taking like 168 hours from the history from like similar time frame, and we're applying that, error pattern to all these, components, and, creating that Monte Carlo simulation. So if you go to the next slide, so the left-hand side is really the output. It almost, it is a distribution. So we are, from each Monte Carlo draw, as described earlier, so each Monte Carlo draw, that gives us a net load for each hour going forward, for 7 days or 168 hours. So we are calculating the net as a, like, load minus solar and wind, and we are bringing the COP data And using that COP data and net data, we can calculate the capacity margin, and that's also a distribution. So we have distribution for each hour going forward for 168 hours. And the right-hand side, this is a kind of product that we are envisioning right now. So it really shows like they're supposed to be 3 lines, but if you look at the left-hand side, the probability of margin being below 3 gigawatt is nothing, it's 0, because I realize that fonts are really small, but the left-hand side plot that has like a step of 10,000 megawatts. So you can see that the probability of the margin below 3 gigawatt is 0, and same is the case for probability of being the capacity margin being below 5 gigawatt is also 0. Now, so if you can see that some of the probabilities does have some numbers. So probability of margin being below 8 gigawatt, 0.5%, probably our 8th hour from the time that we ran this, and the pink is showing some probability that the probability of the margin going below 10 gigawatt is 2.5%. Probably that's too large for really making any decision, but we are thinking like that's up in the air as of now. Like what would be the threshold that we want to flag that hour from this simulation. All right, so while working that in this project, we are faced with some challenges, and I know first one is that the actual basis distribution of the forecast is unknown. So we are getting the forecast from the vendors, especially for solar and wind, and we're getting like 2 points, P50 and P20. So we really don't have visibility of what's the basis distribution that formed that probability. So we're just assuming that's a normal distribution, and that's probably the easiest and most universal. And the other challenge is that error patterns are not straightforward to predict for the forecast window. So we just have to rely on the history, and we have to just assume that, okay, history repeats itself. So especially for solar and wind, so we just have the top level view, what's coming as at a forecast. So we can just see like, what's on the top level at the group, but what's going underneath. If the vendors change, replace a ladder with an elevator, we don't have visibility. So we just rely, history repeats itself. And there is a possible cross correlation on autocorrelation between all 3 components, but that's we are not explicitly analyzing it, and we are utilizing Monte Carlo simulation, and we are not breaking that cross correlation and autocorrelation because we're drawing the samples from straight 168 hours. So if there is any autocorrelation and cross correlation, that will be captured by the Monte Carlo simulation, but we haven't assessed that explicitly. That's the assumption is that that's going to be captured implicitly. And the other challenge is load solar wind capacity is dynamic, so it's changing. It's constantly increasing the capacity. So 400 megawatt error yesterday may not be equal to 400 megawatt tomorrow because the capacity is changing. So how we are dealing it? We are simply normalizing everything by the installed capacity of the load level, and we're just in the later process we're applying the capacity again. All right, so with that, happy to take any questions.